Welcome back, everyone. This is session 5 of the developer training for HiPAS Gridlab-D, and today's session is going to be going into details about modules and classes and the kind of capabilities that you find in each of the modules and the classes that they support. Before we get into that, the first thing I'd like to do is just look at the exercise from session 4. If you recall, the goal of this exercise was to write a validation test for an integrator in Gridlab-D. So you would want to write a test in a manner that would be compatible with how the validation suite works. So what I'll do is I'll kind of go over each part of this, give you a sense of why it's done the way it is and how it works. If you recall, one of the tricks that we talked about in the last session was the header type for CSV files. And since we're going to be generating output in a CSV format, it's very convenient to use this particular header type, which only contains the name information, because if you use the default header type, it includes a timestamp that basically tells the system or the reader of that file when the CSV file was generated. And of course, if you're generating a CSV file for the purposes of doing validation, the original file will have the timestamp associated with when that file was originally created. And the test file that you generate when you run validation will have a timestamp of when you run in the validation. And naturally, those two won't match. There are ways to tell the diff comparator that we use, which you can see down at the bottom of this example, to ignore those lines, the comment lines. But I find it's much more convenient simply not to output those lines at all, since they're not particularly important for the purposes of validation, and simply tell the CSV header type to be the column names, and that's it. And as you see in this particular example, you can see the output just contains timestamp input and output, and no other information, which is really handy because that's generally what most readers of CSV files expect to see. The next thing that you find in this solution to this exercise is the clock settings. And here I just set it up to run one day. To run a test like this, where we're doing 1 minute increment, it really isn't necessary to do more than a day. If you do more than that, it just takes a long time to run the test. And I don't think it really qualitatively improves the test any. It's going to depend on the type of test. Some tests do require longer runs because of the nature of what it is that you're trying to validate. But in this case, we're going to run a one minute time series increment. The time step is 1 minute. So 1 day is going to give you ample amount of data to run this test. The next thing that's in here, this set random seed equals 1, is really important. If you think about how random number generators work, by default, Gridlab-D uses an entropy source for its random number generator. So if we were to create a reference validation test and then later run that same code again, we'd get a different random number sequence. And since we're going to use random numbers in the class, as you can see below in the class definition, as the input, we'd like that random number sequence to be repeatable. And so the best way to make it repeatable is to set the random seed to some non-zero number. In this case, I just chose 1. It doesn't really matter, as long as the number is not 0, which is what you use for the entropy source in Gridlab-D. This sets the random number generator sequence to start at 1. And that means it'll be very repeatable. Every time you run Gridlab-D, you'll get the same random number sequence for each object. And in this case, that's what we want, because we'd like the test to be repeated exactly as it was when it was originally generated to produce the output that we're going to compare against. The next thing is the filter itself, and the definition of a discrete time integrator is 1 over z minus 1. And in this case, we set it to have a 1 minute time step. So you can see here the 60-second time step is specified, which basically is telling Gridlab-D that it should update the filter every minute and calculate this transfer function for the input to the output. And this transfer function corresponds to integrator, which is why we call it integrate. And as you'll see later, when we create the object, we will use that integrator to generate the output. So next is the definition of our test class. And in this case, we're going to use, like I said earlier, a random number generator to generate the input signal. And then we're simply going to create a double for the output. And those are the only two variables that exist in this class. And that will be ample for what we're looking for and take care of everything that we need to handle in that particular object. And so the next thing we do is we define our test object. And here I'm going to use a normal distribution with a mean of 0 and a standard deviation of 1, so a standard normal as the input signal, and I'll update that every minute, which is all we need to do in order for the integrator to have a new value every minute that it can and then integrate every minute. The output is then set to the integrator reading the input. So this basically takes this Z transform that we defined here and calculates the output based on the input, which is exactly what we need for the purposes of this test. And next we implement a recorder that just records these the inputs and outputs again every 60 seconds and saves them to a file called integrate.csv. And then finally, if the integrate.csv file is found in the parent folder, we run the comparison of that one to the one that we just generated. And this is essentially what we do for the validation system to work. So when we run the GLM file in the parent folder, which is where the auto tests are stored, it generates the test integrate CSV file that will be used as the reference, the thing we look at when we're trying to verify the results. And when we run the validation sequence, it's run in a subfolder called test integrate. And so if we find the CSV file in the parent folder, that means we're running a validation test, and we simply want to compare the two. And if they're different, we'll store the difference in this gridlab-d.diff file. And of course, that would cause the test to fail. And you can see here the output that's generated. You can see that the initial value of the input is created 0.44. And then, of course, the integration, the next time step, that value is then picked up and stored in the output, and a new value is generated, which is then added to the output. And you can see over time, what we're getting is a random walk. So this is how you would create a random walk value, given that there's no random number generator that actually creates random walks, right? So you just take your normal distribution, you integrate it, and that gets you a random walk. So this is an example of a very simple validation test. And this is basically how these things are constructed. Obviously, these can get much, much more complex. And if you look at some of the validation tests, for example, in the power flow module or in the residential module or the generators module, they're much more extensive and have a lot more objects interacting with each other, but it's always the same idea, right? We create a bunch of objects to perform a certain task. We generate output and we verify that that output is the same as it was previously. And if it is, then we know that the software is passing the validation test. So with that, hopefully that gives you a sense of how we create validation tests and gives you a good example of sort of the kinds of things that you would expect to see in most validation tests. All right, so let's move on to the topic for today, which is modules and classes and the features that are available in each of the modules. We're going to cover a whole bunch of modules. So there's a lot of material to cover today. We're going to first talk about the tape module, which is one of the oldest modules in Gridlab-D. It provides a mechanism for playing values into objects and recording values in objects out to CSV outputs. Next, we'll talk about the climate module, which is used to handle weather data. We'll talk about the 3 loads modules: residential, commercial, and industrial loads. Then we'll go into some depth on the power flow module, talk about the different power flow objects that exist in that module. We'll talk about the generators module, which provides various objects that can be used to inject power into a power flow network. We will spend a little bit of time talking about the revenue module, which handles billing and tariffs. And then finally, some extensions to the tape module or variations on the tape module to work with databases and record data in MySQL and InfluxDBs. Just by way of background, there are a number of command line options that are available to help you work with modules. The first, probably most useful one, although it's not widely known that it exists, is the one that lists all of the available modules that are installed in your version of Gridlab-D and where they're installed. So if you just use the mod list command, it will read all of the libraries in the Gridlab-D library folder, and all the ones that are compatible with the current version of Gridlab-D that you're running. It will tell you what version they are and where they're located and what its name is. So this just gives you the ability to find out what modules are available in the version that you've installed. If you want specific information about a particular module, the libinfo command allows you to get that information. Most modules are fairly simple, and so this command line option will give you the names of the classes that are implemented and the list of the global variables that are available in the module. Some modules have very extensive lists, others just have a few, like this climate module. Next, and probably the most commonly used one, is the mod help. This gets you help information about a particular module and a class within a module. You can give the command without the class specification, the part after the colon, in which case you get a list of all the classes. But if you provide it with the class specification, you'll get a list of the global variables that that class might use, and a list of the properties that the class uses, including information about whether the property is required, whether it's an output, if it has a default, that kind of information, as well as in the case of things like enumerations and sets, each of the keywords that are supported. So this gives you a pretty comprehensive view of what each class supports and what properties are available to you. Another useful command line option is the example command line option. In this case, what it does is it outputs the definition for an object, and it outputs it in a manner that tells you, gives you a sense of what the default values are. So if you were to, if you needed an example of the object definition itself with the values that you would get if you were to not set anything, this gives you the ability to see what those values are and potentially decide whether or not you need to set it differently for your particular application. Finally, of course, there's the online documentation, which is available in the module folder in the table of contents. So if you click on module, you'll get a list of all the modules that are available. And of course, you can click on the module documentation itself, or open up the module folder and get a list of each of the classes that are available in that module. So that online documentation should be fairly complete. We have noted that there are some that still have some to-do items. Those should be wrapped up and completed by the end of the development effort on Gridlab-D 4.3. Okay. So let's jump into the tape module. Sorry, I think I'm losing my voice. Probably not the best time to do that. So the tape module is, as I said, the module that's used to record values in properties and to play values into properties. There are actually several types of recording mechanisms, so we'll talk about those in general, and talk about the differences between these different recording mechanisms. But at the module level, the main thing to remember is that there are a couple of module parameters that affect how the recordings are done. And sometimes these are very important if you're working with Gridlab-D live. Right? If you're running a simulation and you want to look at the output while it's being generated, you may need to use either of these parameters, the flush interval and the CSV keep clean, option, which allows you to make sure that the CSV file always has a complete line in the output. Because file output is buffered, it's possible that you could get a partial line for some time in the CSV file. And so these two can be used to make sure that that doesn't happen. You can either request that it be flushed every, say n samples by using -n as the flush interval, or you could simply instruct it to make sure that the line, the CSV output is always clean, and it always ends at an end of line rather than somewhere in the middle of a CSV, which might disrupt a reader. We've already seen the use of the header type. CSV data only is just a variation on that, which uses an integer rather than a keyword, but it's otherwise exactly the same thing. It affects the format of the output and determines whether the output includes the comment fields or just the names of the headers or nothing at all. And all three are potentially used in Gridlab-D depending on what type of tool is reading the output. So we talked a little bit about recorders, and we'll get to them in a little bit more detail in a second, but let me first talk about players. So these are the objects that are used to play values into other objects. And so here the basic idea is you specify the properties that you want to play values into. Those should correspond to columns in your file. If you don't specify that, it will read the first line and use that as the list of properties to play into the object. So if your file already contains all the properties that you wish to play into the file, then you're all set. You just have to specify the file name and nothing else. That will take care of everything for you. But if you don't want to use that header, or you want to, or it's not existent, it's not available in the file, then you do need to list the properties so that it knows which column gets played into which property in your object. There's also a loop option, which allows you to loop back and play the contents again. This only works if your CSV file contains what are called delta times instead of timestamps, which are permitted. So your first record must be a timestamp, but it's possible afterwards to have only delta time steps as your time step. And what this effectively allows you to do is play a series of values in repeatedly, where it goes back to the beginning of the file when it hits the end and continues to read these time steps. And you can essentially indefinitely play this loop. And what the loop parameter does is it limits how many times it will do that before it stops doing it, and most likely effectively stops the simulation. So this mechanism is really useful for generating a sequence of values that is then played repeatedly into an object of some type. So that's basically it for players. Players are pretty straightforward. There is a limitation on how many players you can put in a simulation. It actually has to do with how many open files you're allowed to have in on an instance of, say, Linux or Mac OS or Windows. Generally, that number's 1024, but you can increase the number of available files. It's generally an option that you can set on your operating system. Alternatively, what you can do is use one player to play into multiple objects using a transform of some type. For example, a Z transform that either copies the value or rescales the value, or put some kind of a filter on the input player and then plays it to other properties. And that's relatively straightforward to set up if you need to. The next type of object that is available is called a collector. A collector is a special kind of recorder that records an aggregation of properties rather than simply recording the property. And so you do need to specify the property, but the properties have to include the aggregation function. So you can see here in the example, the property that's listed is the air temperature of a house, but what we're recording is the minimum and the maximum air temperature observed within the hour interval that we're sampling. There are other aggregators. You can record average, standard deviation. There are a few other aggregates like median. I'm trying to remember off the top of my head. I think some of the other higher moments of statistical moments are available as well. But the idea is that we can sample periodically and collect these values in aggregate over that interval and store that in the file. You can also limit which type of objects are being looked at using the group characteristics. So you can specify, for example, group class is equal to house. And so then it would only collect these characteristics over objects that match the group, in which case the parent is no longer relevant. You would not use that. You would simply specify the group and it would look at all the objects that meet that group. So that's allows you to look at aggregations over collections of objects. So that's pretty straightforward. That's about all there is of significance with respect to collectors. I will mention triggers allow you to start recording when a particular value reaches satisfies some condition. So the recording essentially is held off until this property meets that condition. And that's a useful thing for triggering on a fault, for example, or an error. But it's not used very often. I don't find that it's something that's used very commonly. And then the flush mode, you can identify the flush mode for a particular, for each individual collector rather than the flush mode that's applied to the entire module. And essentially that just does -1 means wait till the output buffer is full. 0 means flush every single time we generate a new row. And greater than 0 is just to wait a certain number of seconds between the flush operations. Okay, so recorders is probably the one that's most widely used in Gridlab-D. And in this case, it's very similar to the collector, except that it records individual properties. It doesn't do any kind of aggregation. One thing that recorders are very good at is handling units. You can specify the unit of your output that is different than unit for your input. You just do that by specifying the desired unit in square brackets after the property name. So for example, here's a air temperature and mass temperature, which in the house object are stored in degrees Fahrenheit. And by putting the property with units of degrees Celsius, it just converts them automatically for you and generates them in Celsius rather than Fahrenheit. And so you can do that for any property. And of course, you have to be consistent about your units. If they're incompatible units, it won't work. You'll get an error. You can choose to output either a new file when the simulation starts or append to an existing file, which allows you to essentially gather together values from multiple objects or multiple simulations in a single file, if you so desire. Otherwise, the rest is similar to the collector, with the exception of the formatting of the date time column, which is the first column. You can actually specify your own date time format in a recorder. In addition, you can ask the recorder to include the units either on the header itself or on the individual outputs on each line. And you can specify that these are done by for all of them or for none of them. And of course, the default is different, but this is the legacy values that the header is not included. The units are not included in the header, but they are included in the values output on their individual rows. If you're reading, for example, data into pandas, you may want to set the line units to none and set the header units to all, so that you can see them in the column names, but not in the data itself. And that's, of course, the opposite of what Gridlab-D does by default. So this is just something to keep in mind that's available to you if you're trying to write data in a format that's different than the defaults that Gridlab-D normally uses. Another very important and useful class that's not widely known is the histogram class, which allows you to generate histograms of data. So it's essentially a recorder that looks across, much like a collector, across a group of values, but it will record the number of observations of the value within each of the bins that you specify. So it's otherwise the same as collector in the sense that it uses a group and it looks at certain properties within the group. But you have to specify the binning mechanism that you're interested in, either the min and max values of the bins themselves, the bin counts. And you also have to specify the rate at which you sample those bins and the rate at which the bins are counted and written out, which are two separate rates. And then, of course, there's a limit on the number of records that you might want to output, and you can specify that limit. So these histograms are useful for general sampling of objects in a particular class, for example, to see how many objects have properties in different ranges. There is a group recorder, which basically allows you to record values across a set of objects that have a group characteristics, like a class and so on. In this case, it's very similar to the recorder, but it's got some additional features. Curiously, it doesn't have exactly the same features as recorders. It comes from a different implementation. But you can see it's generally got the kinds of things that you would expect to see for recording values across large sets of objects. The results of this, however, can have a lot of data associated with it, because you can imagine, you have potentially hundreds of objects that satisfy the group characteristics. And so it's implemented in a way so that it's efficient, but it can generate an enormous amount of data. Okay, so moving on to the climate module. In this case, the module is designed to allow you to read in climate data into objects that need it. Not all objects require you to explicitly identify which climate data you have. Many of the objects will assume that there's just one climate data specification for the entire simulation and will read that one. Some objects do allow you to refer to specific weather data, meaning that you can actually have many weather recordings within a single simulation, and different objects will refer to different ones, allowing you to have highly localized weather data. This is particularly useful for solar and wind, which can vary pretty significantly across relatively short distances, depending on where you are in the country. And in California, that's a particularly common thing. For example, in the Bay Area, we have a lot of microclimates, and you don't have to go far to see completely different weather. And we can handle that with weather data that's specific to each object. So climate data is data that comes from NREL. It's typical meteorological years. So you have to keep in mind that these climate data sets are essentially weather recordings that have been aggregated from multiple years of data, where each month is the most typical or a representative, think of it as a centroid, for all of the observed weather data in, say, a roughly 30-year time range. The result of this is that it's actually a pretty boring weather data set. Doesn't have a lot of extreme conditions, if any. And so it's not particularly useful for certain kinds of validation. It tends to be very good and very useful for getting your average energy use, but it may not get you your average power, because it's not the centroid with respect to things that necessarily give rise to the power behavior, but they're more oriented towards the energy, which is the integral. So that's just something to keep in mind when using TMY data. The other thing that's important to know about TMY data is that you may find step functions or big steps in temperature at the end of a month going into the next month. So for example, you find the temperature on January 31st at 11 p.m. is significantly different from the temperature on February 1st at midnight. And that step can be disruptive in a simulation, depending on the kinds of things that you're looking at. So that's just something to keep in mind when using TMY3 data. Otherwise, the coverage of TMY3 is really good. So there's a lot of data that's available, and it's used as the basis for the NSRDB data set that we use for getting weather data for a location, although not not completely, right? There are differences between the NSRDB data from NREL and the TMY3, but they do originate with the same data sets from NOAA. The other thing that's important to know about TMY3 data is it calculates a bunch of metadata and derived information that is necessary for a lot of Gridlab-D simulations, including all of the solar fluxes for each of the orientations. And so horizontal, north, northeast, east, and so on, as well as the global diffuse values for solar fluxes. It also generates the design temperatures that are needed to do HVAC sizing calculations. And when we get to the house module, you'll see an example where that is necessary. That information is useful and is necessary for doing sizing of the HVAC systems. Other data sets that use the weather data don't do this. They don't provide those kinds of metadata that might be needed for doing things like house sizing. And so that's a consideration when you're choosing which weather data to use. So for example, when you retrieve NSRDB data using the tool that's provided, you're not going to get HVAC sizing data as part of the data that comes in, which means that the house module may not size the houses correctly because it doesn't have access to design conditions that are normally used for those calculations. So just something to keep in mind when you're working with the climate module. When you use the climate module, sometimes you need to specify the path to where to find the climate data files. Normally this is set automatically, but if you are using your own library for weather data, you may need to specify the path to that library. One thing to know about the modules that we're going to be talking about from here on out is they use a more advanced API. The tape module is one of the oldest modules, and it uses an API that's fairly simple. The climate module and all the other ones we're going to talk about uses a more advanced API. And this advanced API includes the ability to control the output that's generated by the module separately from the output that's generated by the core. And you control that using the message flags. So you can control warning outputs, debug output, and so on. Normally, these outputs are disabled when Gridlab-D is running, but you can enable them if you want and generate more output from a specific module if you need to. All right, so the climate object itself, most important and it's required, is the TMY data file name. That's the name of the file in the library. If you use the weather get command, those are the names that you would refer to here. So you'd say, for example, weather get California San Francisco International Airport, and then that's the TMY file that you would specify here. Once you've specified this, everything else is populated automatically for you. So you don't have to specify any of the other things other than perhaps some things that control how values are calculated between, for example, the interpolation. Normally, Gridlab-D does not interpolate the weather data, so the value that's observed at a particular moment in time remains with a zero order hold until a new value is observed. But you can change this to do linear interpolation. So if you were to stop the simulator at some point between two samples in the weather data, you would get a linear interpolation of the temperature. You can also do quadratic interpolation. And for some values, this makes sense. You should be a little cautious about using quadratic because it can generate values that don't make sense. For example, when you do quadratic interpolation on solar, you might end up with negative values when it drops down to zero because the quadratic fit of 0, 0 and another number might not make any sense. And so that can lead to situations that produce numbers that don't make sense for a particular type of data. So here are all the solar values that are available to you. The position of the sun in the sky, the total irradiance, the different parts of the irradiance, how it breaks down, and then of course all the irradiances by orientation. One value that's particularly important for some modules is ground reflectivity. if the ground is highly reflective, it can increase the solar radiance on certain surfaces, and having that value available does improve the quality of some of the energy calculations, heat gains in particular. And not many data sets, climate data sets, provide ground reflectivity. And of course, reflectivity could change significantly during the course of the year, but when it's available, it does improve the quality of results. Some other aspects, features of the module include a reader. Allows you to specify a different weather reader for the climate object, and we'll talk about the CSV reader in a minute. And then, of course, all the other metadata that's collected, record low, the day on which the record low is observed, the record solar. You can have a cloud model. The cloud model is bulky and compute intensive, and it will definitely slow your simulation down. But it does provide the ability to get highly detailed solar behavior, very granular solar behavior if you want to use that. And so that's particularly useful if that's something that you need to capture, for example, with PV generation. And then these are just the values that are associated with the use of the cloud model. The CSV reader class just allows you to use an alternate input file, a CSV file, and feed it through the climate module so that you can get from a regular CSV recording all the metadata that you might want associated with a TMY file. So you can basically get a CSV file to act like a TMY file if you have a recording, but you need all the metadata, design conditions, solar calcs, and so on. If you want to just read in raw weather data and you don't want to go through the climate module, there is a class that implements weather directly. The other thing you can do is just create this class yourself. You don't need to load the climate module, since the only thing this does is make the data available to other objects. So you can create your own custom weather class if that's your preference. And in fact, the NSRDB weather tool, the NOAA weather tools, all do that. They actually create the weather class as a runtime class instead of loading the climate module. It makes no difference. You can do it either way. But it's just, this is a utility class that gives us sort of a reference definition that we can all rely on and count on having available. All right, so jumping then into the residential load module, we're going to do 3 load modules fairly quickly. There's an enormous amount of information in these models, in these modules, and of course the model for the house in particular is extremely detailed. We don't have time to get into all the details, but I'm going to give you a quick overview of how it works. So the house model itself defines the thermal behavior of a house as a physics-based model. And within that, you can define a wide variety of appliances. You don't have to. If you don't, you can ask the house model to implement simple appliance models that get you the right load shapes, and without going into the details of modeling the individual appliances. And then the way the house model works is it expects to be connected to a meter. You don't have to do that. You can define a house without a power flow object to connect to, but you'll probably get a warning, something to the effect that there is no voltage source, and so it's going to use a static voltage source, which is fine. It's a warning to let you know that the house is not connected to a power system, and so it's going to simulate it as though it were with some simple default values. If you think about it in terms of the structure, the class hierarchy, houses are derived from a residential end-use model object, which implements all of the end-use loads. And then the house implements a panel, a distribution circuit within the house for each load, end-use load. It's connected to an individual circuit. It has a limit, current limit, say 20 amps or 30 amps or 50 amps. And then the house panel itself has a circuit limit, typically 200 amps. And that is what's connected to the meter. And so that whole infrastructure allows us to monitor individual loads and see whether any loads are exceeding the limits of the infrastructure that we have in place. As you can imagine, this is very useful for things like electrification studies, where you're concerned about whether you exceed the limit of the house panel as you add new loads onto the house. The residential building module also includes an apartment building, which is still in development. And that is essentially multi-tenant rather than single family home models. There's also a data-driven model that uses the RBSA, so that's the Residential Building Stock Assessment that was created by Ecotope about 5 years ago. There are other sources of implicit end uses. So these are the end uses themselves that can be used to avoid having to model appliances explicitly. The original data set from Bonneville Power Administration is called LCAP, and there are two versions of it, one from 1995 and the other from 2010. They're quite different. End-use loads have changed quite a bit since 95, and in fact, they've changed quite a bit since 2010, which is why we also have the RBSA implicit end-use load shapes, as well as the more recent EIA load shapes. Those are all available, and you can choose which one you want to use. I believe the default is the 2010 LCAP load shapes, but I'm not positive about that. It might be the EIA 2015. So that's basically how the house model works. The apartment building models is fairly similar, but of course it's multi-tenant, and the appliances are not explicitly represented anymore in the apartment buildings. The module itself has a lot of options. There's in fact no room to list them all out. I do recommend that you take a look at the list. Some of the most important ones are obviously the default line voltage and current, and basically the various power system settings, as well as the default climate when there's no climate settings, and then a duration limit on the solver that's used to solve the thermal model in houses. I've actually never run into a situation where I need to set that parameter. I believe the ETP solver is very stable, and I don't think it runs into problems. So yeah, I've never had occasion to need that. In addition, there's an option to set the ANSI voltage checks to verify whether the houses are going out of spec with respect to the ANSI voltage 5% limits. One widely used one is which implicit end uses you're going to enable. If you are modeling appliances explicitly, you need to remove them from the implicit list of end uses. Another convenient thing to do is if you want to model just HVAC, you can set the implicit end uses to none, and that disables all the other loads in the house, and you will see only the HVAC system operations. And then, of course, you can choose which end use source you want for your implicit end uses. And as I said, I believe LCAP is the default, but I'm not positive about that. Some other globals that are potentially of use are some flags to specify whether we get warnings at particular temperatures in houses, and things like how long do the controllers, the thermostats, dwell before they allow changes in the settings, at what temperature does the auxiliary heating cut in. There's also some features to allow you to dump the circuit panel, which gives you the currents and I think voltages on each panel circuit. So you can get a breakdown for each house of what each end use is doing. And you can specify the interval at which this is done, and the resolution, the time resolution at which the panel dump is performed. There are also some options to control how the sump pump behaves in the house, because that's quite that's something that varies significantly regionally, but is not really available in any other source. So we have to specify it at the module level. And in addition, some end uses can be curtailed if you want. And so you can list out which end uses are curtailed and whether that curtailment is active. And this is done globally at the level of the entire module. So you can imagine having all the houses on a feeder go into a particular kind of curtailment event, let's say hot water heating curtailment, and specify which end uses, that hot water heater is the end use that you want curtailed, and you can specify when it's curtailed. If we look at the end use itself, this basically allows us just to get details on the behavior of each end use in the house. So lights, plugs, heating, cooling system, hot water, and so on, each of the appliances. And as you recall from the list of implicit end uses, there's quite a few of them. And you can get information about each end use, what its source load shape is, what its load characteristics are, and then its behavior. How much energy has it used? What's its current power? What's its peak power? How much heat has it delivered to the house? And so on. So all of this information is available for each circuit in the house. Here's an example of the module parameters that relate to the RBSA model. So we've talked about the physics-based model. Now we're getting into the data-driven model. And so the data-driven model works by reading load shapes that are associated with months, days of the week, hour of day. They may have, voltages associated with each of the loads, because the load behavior is sensitive to voltage. And then they may also have other conditions that relate to its sensitivity to temperature or solar gains or price. And so we can set those default sensitivities for any data-driven load where we want to have some kind of demand response represented. So here's an example of data that comes from RBSA that provides the load shape for each end use that you would find in a house for each month of the year, for each day type, weekend, weekday, holiday, and each hour of the day. And so that data is collected from houses in a survey in the Pacific Northwest, and then can be used as a data source. If you have a different data source, you can certainly add it to this data set. It's not a problem. The data set itself is maintained in the RBSA data repository and is always available to everybody. It's a public repository. The class itself that implements this, really, mostly it just needs the file name and the load composition. We'll talk about how load compositions are defined, and the floor area of the building so that it can scale relative to the floor areas in the survey. And then it will tell you, it will output information about the total power. You can also give it a weather and a tariff object so that it can get temperature, solar, and price information. If you don't include these, then it simply won't be sensitive to weather and price information. It'll just be sensitive to voltage. So this is how load composition is done. Essentially, for each end use in the house, we can specify the real and reactive constant power, constant current, and constant impedance components, and what fraction of those components contribute to each of those. As a general rule, the real power components need to add up to 1, but the reactive power ones do not. And effectively, what this gives you is the power factor for each of these end use and the scaling of the load shape into that end use. So the floor area provides the bulk scaling, and then the load composition provides the scaling with respect to the voltage sensitivity. So that's basically how it works. There's examples that you can look at in the auto test, for example, and there are examples in the documentation to that particular object. Okay, so for commercial buildings, small office buildings are essentially done the same way as houses, except that they have rooftop package units instead of heat pumps or various other kinds of heating and cooling systems that you find in houses. But otherwise, they're essentially the same in their structure and how they are defined and used. If you want to use a data-driven model, you have to use the California Commercial Building End Use Survey, so CUS. It's very similar to the way RBSA works, except that it includes climate zones and building types. So where RBSA basically has one type of building, a house, CEUS has many types of buildings and many climate zones. But otherwise, the sensitivities are going to be the same for the load composition for voltage. But you have additional sensitivities for the heating and cooling system, the solar gains, the price, the occupancy sensitivities. Those can also be included in the load composition, which gives you a much richer response for a commercial building model and allows you to take the CEUS data and have it adjust the load according to weather, according to voltage, according to price and solar gains and building occupancy, if you so desire. So here's an example of a CEUS object reading from forecasting climate zone 1 in California for a small office building, 50,000 square feet, arguably not that small, but it's perfectly okay. And then, of course, if you want, you can specify your tariff object, and we'll talk about those in a little bit. And then, of course, your weather object, which refers back to the climate module. And then you can specify all the sensitivities for the real and reactive power, current, and impedance, as well as the heating and cooling temperature sensitivities if you want for each of the end uses. Generally, if I remember correctly, you must specify the composition for each of the end uses that are available in the load composition from CEUS. So these are all that are available right now. I believe if you leave it out, it will either issue a warning, it might even issue an error. So you should generally include them all. If you want to zero out a load, you can do that just by specifying 0 for everything, and it won't contribute to the total load. Another object that's now available in Gridlab-D for commercial buildings is parking lots. And the reason this was added is because of EV chargers. Generally, lighting is not a major consideration in parking lots, but as a part of the definition of the parking structure, we included the lighting and ventilation portions of the parking structure, but really the most important load is the chargers themselves. And so this allows you to specify how many chargers are installed, how many of them are, what fraction are active, what the power of each charger would be, and then observe what the total power consumption of the parking lot is as a function of all of these contributions. And so it's pretty straightforward. Of course, the question is where you get this data, and that's something that I think people are still working on. We're beginning to get more and more data about parking lots and commercial electric vehicle charging infrastructure, and this can be used then to model the behavior of the system in response to those. The third type of load is industrial loads. Here, we've kept this very simple. Industrial loads are highly idiosyncratic. So each industry really has its own behavior. And so trying to model the industry itself doesn't make a lot of sense. So instead, what we use are the NAICS codes. And the NAICS codes are used to describe the general characteristics, electrical characteristics of that type of industry. And then we specify just the size of the customer and perhaps some adjustments on the power factors if we want. So really the only thing we need to specify is the source of the NAICS data for each industry. If we need to, the parent load property that we want this power to be applied to. So let's say a meter object, you would apply it to the properties, the power properties of the meter object. Here's a list of all the NAICS codes that are currently in Gridlab-D's list. Obviously, there's a lot more industries out there. These were taken from the NERC load modeling work group. They have defined certain key industrial loads that are of particular interest in power systems modeling. Mostly this comes from the fact that they run a lot of motors, or they have very significant loads of a particular characteristic. For example, an aluminum smelter has an enormous amount of constant impedance load, whereas other plants might have significant amount of motor loads, And so that composition is very important to capture. That's what determines the way the total load is broken down at a particular moment in time. So this information is available and it can be expanded relatively easily. If you happen to run into an industrial application that's not listed, if you know these components, let us know. We can add them easily enough. Okay. I'd like to take a give everybody a chance to take a few minute break. So I'll stop recording here for a moment and I will take a look. Okay, so the next module we're going to look at is the power flow module. This is by far the most complex module that Gridlab-D has. It's the module that solves power flow problems on networks, and so it has a large number of objects and a number of solvers that are used to solve the network problem under different configurations. So the module itself is relatively straightforward to use for simple problems. When you get into much more complex networks, it can become quite challenging to use. So there are some tricks that we'll talk about as I go through this to help work with this module. The important thing to understand about the design of the power flow module is that fundamentally it really only understands nodes and links. As you might imagine for power flow solvers, this is the fundamental object type that you have to work with. Nodes being the point at which you have power injections, and links being the point at which you describe the impedances and the connections between nodes. Once you've defined all the power injections and the impedances, the power flow solver then can calculate the voltages on the nodes and the currents on the links. That's just about it. There isn't really much more to it than that. Of course, for those who've tried to implement power flow solvers, there's a lot more to it than that. But the idea behind Gridlab-D is to hide as much of that as we can from the modelers by allowing you to define objects that are either nodes or links underneath, but we think about them in terms of the actual objects that we work with, and Gridlab-D takes care of generating the node and link information for you. So that's what we'll actually spend most of our time talking about, are the different power flow objects that are derived from the nodes or links. All of this is used to populate the data that is used by the two solvers that are available. For most of us, Newton-Raphson is really the solver that we should prefer to use. It's the most general, but there are cases where the Newton-Raphson solver is slower than necessary. And you can use, for radial networks, you can use a method called a forward back sweep. It only works for radial systems, unfortunately, but it is generally much faster. One important thing to note is you can actually get away with using the forward back sweep on non-radial networks topologically behaving like radial networks. So for example, if you have a mesh network where the switches are open in such a way that the network looks like it's radial, you can get away with that. But generally, I don't bother. I just leave everything in Newton-Raphson and it seems to work just fine. And that gives us the most general solution and the most flexibility. There are also certain features of the power flow module that do not work in the forward back sweep method. So if you ever run into an error where you're trying to do something and it says this doesn't work under FBS, that's what that's referring to, is that the forward back sweep method has certain capabilities, or it has certain limitations such that certain objects or certain properties of certain objects are not possible to solve. And so in those cases, you will have to switch to the Newton-Raphson method. The other thing to keep in mind is that both node and link are derived from a more fundamental object called a power flow object. This power flow object defines two properties that must be known to all elements of a power flow network, and that's the nominal voltage. That's the voltage used to do per unit calculations, and the phases on which the object is operating. And we'll talk about the nominal voltage and phase a little bit more detail in a second. But let me first kind of run you through the object hierarchy, so you have a sense of the visually a sense of what's going on. Dotted line means you can't implement the object directly. So interestingly, you can directly implement links and nodes without creating the derived object. What this means is that if you have an object that doesn't exist in the object hierarchy, but you still know how to represent it as a link or a node, you can do that. And so that lets you deal with sort of the generality that you might need for objects that haven't already been defined in the object hierarchy for the power flow module. But otherwise, nodes support capacitors, loads, and a specific kind of load called a PQ load, which has sensitivities, a meter object, motors, a substation. These are all variants of a node. Obviously, they have properties which are different, but those properties are then used to calculate the fundamental properties of the node itself. And then for links, we have fuses, a variety of types of lines, overhead, triplex, and underground lines, voltage regulators, switches, which also have two subtypes, reclosers and sectionalizers, series reactors, transformers, and variable frequency drives, which is basically just the component that provides the control of a motor. And so those are the classes that are implemented, which are derived from nodes and links and allow you to construct networks with a variety of object types. As I said, every one of these objects requires that you specify the phase configuration. So obviously an object can be on phase A, phase B, phase C. It can be between phase A and B, AC, BC, or it can be involve all three, phase A, B, and C. If you specify N, that means there's a neutral conductor included. If you specify D, that means that the phase configuration is delta instead of a Y configuration. And for objects which support triplex configurations, S means that the line arrangement is different than ABC. Instead, it's line 1, 2 neutral. So this is used for when we do a split tap connection to the network, typically for a single phase service to a residential customer. So those are the phase configurations. Every object must have them. And if you recall from our, when we were talking about properties, you can inherit that property from your parent object if you want to use that mechanism. I strongly recommend that you always specify the phase configuration of the object that you're working with to make sure that the connections are done correctly. Inheriting doesn't always work as you might expect. For example, when you're working through a transformer, delta configuration to Y and Y to delta may not be supported. And so trying to do that automatically might not work out the way you expect. Okay, so let's jump into the node objects themselves. As I said, there are a particular set of useful subtypes of nodes that we use throughout the model. So you can implement capacitors, you can implement loads. This is the most common way of connecting a load to the network. These loads, however, are three-phase loads. I'll talk about single-phase loads in a minute. And of course, PQ load is the variant of the load that allows you to implement demand response, sensitivity to weather, to price, to any other type of signal that you'd like to inject into the load and have the load vary as a function of that signal. And then meters allow you to collect energy, peak load, and other kinds of data that you would get from an AMI system. Motors implement loads that have very particular characteristics like inertia and stalling behavior. And then the substation is just something that allows you to define the kinds of information that would come from a transmission network, like frequency, reference voltage, things like that. One caveat in all of this: triplex nodes are not derived from nodes. They're essentially a special kind of node that is used to implement triplex loads and meters. It's a little quirk of the implementation. I suppose it could have been done so that it was derived from node, but I believe it's not It's never been a major problem for anyone other than the occasional quirk that someone might run into when they're doing class hierarchies. So triplex nodes implement the 1-2 neutral line configuration, and of course a triplex load uses that, as well as a triplex meter. And so those are used to connect single phase loads onto a 3-phase network. But that's the only quirk about nodes. Some important properties of nodes. The bus type is something that generally needs to be specified. I believe the default bus type is PQ. You should have at least specified one swing bus type. I believe you can specify more than one, but I strongly recommend that the alternates be specified as PQ swing, meaning that if the section of the network that particular bus is on is connected to a swing bus, then the load is PQ. If that section of the network is disconnected from the swing bus, that means it becomes the swing bus. So you generally should create your models in a way that if you have switches where you can open sections and isolate parts of the network, one of the nodes in the isolatable part should be a PQ swing bus. Voltages, there's voltage information for any of the elements. So you can look at any individual node voltage. So, phase A, phase B, phase C. I think it includes the neutral as well. And then you can get the real and reactive parts of those if you want. And the same is true for triplex nodes, but they're named 1-2 neutral rather than A, B, and C. There are a couple of other values that are included in nodes, which are relevant to things like hosting capacity analysis and ICA. And these are the voltage and the voltage violation thresholds, both under voltage, over voltage. I don't know why there's some kind of a typo here. That's weird. But yeah, under voltage, over voltage, and voltage fluctuations. So the voltage violation threshold allows you to just specify plus or minus 5%, say the ANSI voltage thresholds. But you can actually have different thresholds for under and over voltage if you'd like to study how often, say, it goes more than 2% over or 3% under, if you'd like. Voltage fluctuation thresholds are basically the amount of voltage change that's tolerated when the DER value is switched on and off. So for example, if you have a 10 kilowatt DER on that particular node, then the voltage fluctuation that's tolerated when you switch it on and off, that's that limit. It's typically 3%. But you could change it if you want to 2%. So, and that can be done at the individual object level if you want. For link objects, the idea is similar. You have a variety of objects that can behave as links, and they each have their own properties associated with the specific function of that object. And then there are some important properties for each link object that are always available no matter what link type it is. The power in, out, and losses on each of the phases, the currents in and out on each of the phases, the fault currents if you're using fault check features, and then the emergency rating, continual rating, and violation rating for current. Those are basically used to produce warnings or to detect violations in the case of hosting capacity analysis. And if there are faults on a link, there's a mean repair time for when that link is repaired in the event of a fault. There are a lot of library objects that link type and node type objects require in order to be fully defined. So for example, overhead lines and underground lines have configurations, and those configurations also would involve conductors. So you might have overhead line conductor information telling you what the properties of each of the conductors in that line is, as well as line spacing information that relate to these lines. I'm not going to go into detail for all of this. There's a lot to go through, and it's quite beyond the scope of what I can cover in today's session. But this is all fairly comprehensively documented by the documentation that P&L produced on the module. In addition, there's pole configuration. We'll talk about poles a little bit later. Regulator configuration specifying, how many taps there are, what the voltage steps on each tap is, and so on. Transformer configuration, which specifies the turns ratios and such. And then triplex line configuration, which specifies how the triplex lines themselves are configured, which is different from how normal line configurations are done. And so all of these library objects, those are generally generically provided either through the converters that create the models or basically developed libraries that come from P&L's efforts over the last 15 years. So there's a lot of library objects for each of these available already. So I mentioned poles. One of the additions to this version of Gridlab-D is the pole model itself, which implements the structural behavior of a pole in response to weather and equipment loading and deterioration, aging of the pole. And so the aging of a pole is very much a function of where we are. So, for example, wood poles in particular, age very quickly in tropical climates, but they don't age as quickly in other climates. And depending also on the type of treatment that the pole got, the aging might go more quickly or more slowly. So the properties include the pole status, information about the pole's tilt and the direction of the tilt, obviously what weather is relevant to that pole, and the pole configuration, which I mentioned earlier is necessary. The year in which the pole was installed so that we have a sense of the age of the pole, and if the pole fails, how long before the pole gets repaired. All of this affects, of course, resilience analysis for which this is used. And then observations of the wind speed, direction, and gusts from the weather at the current moment in time, which contribute to the calculations of the pole stress and the moments of the equipment on the pole itself, which in turn are used to calculate all of the critical information needed to know at what speed the pole would be expected to fail. In addition, all of the equipment loading is calculated and included in the pole. If the pole has a guy wire, the height at which that guy wire is connected is included as well. And that will be used to determine where on the pole the failure might occur. Pole configuration basically includes all the details about the design of the pole. Since this is typically repeated often inside the model, you may only have a few pole configurations and you may have a great many poles that refer to it. That's not at all unusual. And then any information related to how that pole behaves in general, not specifically in a particular location, is included. So obviously all the overloading factors, the design characteristics of that pole, the physical characteristics of the pole itself, and information about the typical repair time and degradation rate of a pole, how it was treated, and the material characteristics. So all of that is included, and that's all used to do the pole failure calculations in the presence of wind loading and all the equipment that's on a pole. Obviously, we have to attach the equipment to the pole so that we know where on the pole and what is attached to the pole. So the pole mount object does that linkage for you. This allows you to attach cables to the pole, attach capacitor banks or transformers or whatever else might be involved, including providing information about the cross-sectional area and how it is offset from the center line and how much it weighs, that kind of stuff. And that's all used to then calculate the impact of wind on the pole and whether the pole's inclination affects, the tilt of the pole affects behavior. So that's about it for poles and what's included. And all of this is used then for the resilience analysis for poles and for lines resting on poles. Some other useful classes that are available in the PowerFlow module. There are 3 classes that are used to dump information. So each time the power flow solver runs, you have an opportunity to dump the currents, the volts, and the impedances, and that information then can be used to diagnose a solution that might not be working as expected. That should help you identify if you've got a load that's not behaving correctly, or a capacitor that appears to not be set up correctly, that kind of thing. There's also an emissions object that calculates emissions impacts. Personally, I've never used this object, so I don't know the details of how to use it. But it seems to provide enough information for you to calculate a variety of greenhouse gas or other kinds of emissions from generators on the system, on your distribution system. The fault check object is an object that you need to use if you're going to have faults on your system. In other words, line contact with ground, or with line-to-line faults, or line-to-vegetation faults. This object allows you to enable verification of the solution to see if there's any situations arising from faults that the solver might not be able to handle, and deal with those in the course of computing the solution. So it's pretty typical to see, for example, a resilience module or a reliability module include a fault check object so that that works correctly. There is overhead involved in doing that, which is why it's not done automatically. It's not automatically included. So it's something that you have to explicitly include. Frequency generator allows you to create a frequency source if you need one. So particularly if you're doing any analysis that involves frequency sensitive loads, this would provide you an opportunity to include the frequency as a part of the model. Generally, otherwise, the frequency is always kept at nominal 60 hertz, and it doesn't change. Line sensor object allows you to define line sensing technology, basically current sensing on lines. That's not an easy thing to do. If you think about it, the current is different at different points along the line because of losses. And that certainly would be true also if you had other, faults and things like that going on. So the line sensor object allows you to specify where along the line you put that object. Load tracker is not something I've used. As I understand it, it provides feedback controls on the load. So I'm not too familiar with how it works. I've never seen anyone use it. So I'm not sure exactly what the use case for it was, but it is present and available. Power metrics just generates, it's one of the metrics generating objects in the system. Restoration allows you to run restoration use cases, and volt var control implements, obviously, volt var control mechanisms for distribution systems. As opposed to simple volt control that you get with regulators. So that's generally what you find in the power flow module. The generators module is very closely related to the power flow modules. It provides generator objects. Generally, if you're using the generator module, you need to include the power flow module. It's a dependency for that module. It allows you to define batteries, but you have to use an inverter to get that battery to work. It also has a number of controllers that are available for controlling different kinds of generation sources, in particular diesel generators. There's also a number of converters, so the inverter itself, which is necessary for battery and PV, as well as a DC to DC converter, power electronics, and rectifiers. In terms of energy sources, there are only two: diesel generators and solar PV. And as I said, the solar PV itself requires that you implement an inverter. And then general energy storage, which is sort of a generic kind of energy storage class, not as specific as a battery. And so it allows you to define sort of more general energy storage characteristics. You could probably use it for things like, pumped storage, or other kinds, like mechanical storage, spinning, what do you call those? Spinning. I can't even think of the word right now. Sorry about that. But basically a spinning machine. that stores energy as a angular momentum. Okay, so I'm going to give you two examples of generators that we find commonly in the kinds of distribution system simulations that we're doing these days. The first is solar PV. And so the way that's done, I've shown it here with embedded objects so that I don't have to deal with object names. But basically you have a meter, like a triplex meter, and of course it has its phase and nominal voltage specified. And then you have the inverter, which has to have the same phase specifications. And really the only thing you need to specify is its rated power. There are a lot of other properties that are associated with inverters, like what its control strategy is and how it shapes the wave. And there are a lot of other things you can set, but this is minimum. It's just specifying its rated power. And then the solar object itself, the PV, is then embedded within the inverter. You need to specify its weather source because otherwise it will simply generate the maximum solar power. It'll assume the weather is perfect every day, which is, an option if you're trying to look at a scenario where you're thinking about the maximum impact. The rated power of the panel, the panel's area, and then of course its physical setup. Its orientation and its electrical behavior, its efficiency, and so on and so forth. And then of course there are a lot of other parameters that you can set up as well, but these are sort of the minimum necessary to get your solar PV to work. So that's pretty straightforward. One thing I will note, you will observe that the inverter is connected to the meter. It is not connected to the house. The house would be connected also to the meter. And so you would find that the house and the inverter are sort of at the same level. There is no circuit in the house for connecting PV, and we'll see that this is also true for batteries. They're still on the meter, but they're not part of the primary circuits for distribution within the house. And so that's just one thing to note. It's just, that's basically just how it works. So for batteries, the implementation is similar, where you have your triplex meter and your phases and nominal voltage. You can specify the bus type, and that may be relevant depending on the generator mode that you choose for your inverter and your constant and your battery. But again, in the inverter, you have to specify the rated power of the inverter and the generator mode. By default, I believe the default is PF. And I don't believe it supports PQ. I've tried it and it doesn't work. Although that may be something that may actually be a bug because I thought it would work. And then of course, whether the generator is online. So you can turn the generator off if you want, or disconnect the battery, and that turns the inverter off. And the battery then is isolated from the system and doesn't operate. As far as the battery is concerned, there are a lot of parameters that you can specify, what its storage capacity is and so on. The critical one you must specify is its generator mode, and the default is PQ. So that's about it for the generators module. So now I'm just going to jump over to the revenue module. This is the module that works with tariffs and billing. So you have to implement your own billing module. You have to specify where that billing module is implemented in your model. So you have to specify a path to that, as well as the billing function that's used to generate the bills. I'm not going to go into the details of how to implement this here, because I'm actually going to use this as an example when we go into learning how to do Python code. This will be the implementation that we look at. There's a lot involved in implementing the Python code for a billing module. There are examples in the auto test for the revenue module, and I'll use those when we learn how to implement module event handlers in Python in a couple of weeks. So here's an example of a specific tariff. I think this is a PG&E E1 tariff. And so, you specify basically the characteristics of the tariff. and those characteristics are then used to calculate the bills. So the tariff model itself is pretty straightforward. And of course, the billing calculations themselves are really where the complexity lies. And as I said, we'll go into those in more detail when we learn how to implement Python code. So here's an example of a billing object itself. So the billing code has to look at the bills on a meter by meter basis. And so any meter for which we want to calculate a bill, we simply attach a billing object. We specify what tariff it's associated with. So you just give the name of the tariff. And then if the tariff has a baseline that is used to calculate the bill, that has to be specified. And then you can specify what day the bill is generated on. And that would allow the billing module then to do all the billing calculations for this house. Again, notice that the house object is a sibling to the billing object. So it's not, the billing object is not put in the house, it's put in the meter, because billing references the meter, not the house itself. So that's about it for the billing, for the revenue module and how it works. And as I said, we'll go into the details of how to write a billing function when we actually learn how to write Python code. The last thing I want to cover is the database modules. And so these modules are used to essentially replicate the behavior that we see in the tape module, but for databases. And the two databases that we support are MySQL and InfluxDB. So if you're working with MySQL, you need to create an object in Gridlab-D to manage your connection with the MySQL server. You can have more than one of these objects, and then in which case you need to tell your tape or your recorder, your player or your recorder object which database connection you want it to use. If you only specify one, you don't need to tell the recorder. It knows that's the one that you should be using. When you specify your database object, you may need to perform some SQL commands during initialization. You may need to perform them after synchronization or after other events like commit, or you may need to perform them at the end of the simulation when you're terminating. So there are some event handlers to basically allow you to execute SQL code to either set up the database prior to the simulation starting, create tables, set some values, insert some records, for example. During synchronization, there are things that you might want to do, like go out and clean up some records, update some values based on other values, things like that. And then, of course, on termination, you might have more cleanup and final calculations and things that you'd want to do, like deleting temporary tables and stuff like that. You can specify the interval at which you'd like to call the synchronization event so that you don't have to call it every time a sync event occurs in Gridlab-D, which could be very slow. And so this allows you to specify how often this synchronization is performed, if at all. Options are things that allow you to specify how this database object is created. So for example, if you use newDB, the database that you're working with gets deleted and recreated. And if you specify, there are other options, for example, to do various things when the database is first connected. With respect to a recorder, it's really not all that different from how it works with tape objects, with the exception that you may run into situations where one recorder is recording to the same table as another recorder, which is totally allowed. If that is the case, you may want to include the object class and ID in your properties rather than recording to a file name that is based on the ID of the object. Because what would happen is with this recorder, you'll end up with as many tables as you have objects. Whereas if you were to include the property class and object name and ID in the list of fields, you get only one table, right? You wouldn't have to include the ID in the table. And that would just be stacked. You'd have all your values listed out. And then you could basically save a lot of time and space and have everything collected in one location. The nice thing about using the SQL, and this is true also for InfluxDB, which I'll talk about in a minute, is that you can have a very, very large number of objects with recorders operating, and you don't run into the problem that you have with CSV files, where you might run into the maximum limit on the number of open files in your operating system. So if your host machine has a limit, say, of 1,000 open files, if you use the SQL database interface, that limit simply doesn't exist. And there's effectively no limit other than the amount of time you want to take and the amount of data you want to collect when you're using MySQL. This is also true with InfluxDB. InfluxDB is a different database implementation. If you're not familiar with it, it's an implementation that basically just records. It's really good for recording time series. SQL is not great at time series. You can do it. And in fact, this is exactly how the recorder works. But querying time series in SQL can be cumbersome. In InfluxDB, it's very, very efficient. And so the InfluxDB recorder can go much faster than the MySQL recorder. And as a result, your simulations will run a lot more quickly. Obviously, you'll have to install your InfluxDB server. That's not difficult to do on most systems, or you can install it on another system and make a connection to the remote system. But again, you have to define your object, your database object, and then refer in the recorder to that connection and what fields you want to record. And because you may have multiple objects recording in the same table, you might have to tag those records. And so the tags allow you to add additional things like the ID, the name, as fields that are used to tag records. So that's basically a quick summary of the database interface objects. I think with that, that pretty much covers everything. I will take questions in a minute. I'd like to, before I stop recording and take questions, I just want to introduce the homework assignment for the next session. And so in this one, what I'd like you to do is record the hourly air temperatures and energy use for the default house. And we're going to do it for Pasco, Washington, and we're going to do it on a specific date, January 27th, 1995, using TMY3 weather data, and just generate a plot of that energy use. And so there's a couple of hints. You know, the weather data to use for Pasco, Washington is actually from Yakima, Washington. So you have to find that weather file. Because you want to record something, you don't want the initialization transient to be part of your data. So I suggest you start the simulation earlier and use the recorder in service field to turn the recorder on at midnight on January 27th. And then just so you know, calculating the energy use requires that you do the differential, right? The difference of energy use from 1 hour to the next, which you can do by looking at the panel energy field, but you're going to have to run it through a difference filter. And so the difference filter is essentially the opposite of the integrator. And so that's what this is describing. So this is the discrete transfer function to get the difference between a value and its the value an hour ago. And that gets you the 1 hour essentially average energy use over from 1 hour to the next. And that's the easiest way to get that value out of the meter object on a house or the panel on a house. All right, so that should be enough, a good enough puzzle for next week's session. So, and I will show you the solution to that next week. And so with that, I'm going to stop the recording and we'll open it up for questions.